Thank you. So as the title of my talk says here, I'm doing a little bit of prediction. And in order to do some prediction, I need to look at the past here. Let's talk about the reasons why we might need anonymity in the first place. We have the internet. It's designed without security, without anonymity, without concern for anyone being bad or needing privacy or, heck, even passwords in the beginning. Most of the anonymity systems that we have out there are all based upon one man's work. Initially, David Chaum's. In the late 70s, this newfangled crypto primitive called public key cryptography was invented, and Dr. Chaum came up with a neat idea of wrapping messages in sequential layers of public key encrypted containers so that you could send them through multiple untrusted nodes and have them be decrypted such that the previous nodes wouldn't know what the contents were. Node A would be sending a message from the sender to node B, not knowing who the recipient would be. Node B would get it, not know where it came from, would send it on to another node, etc., until you came to the end, and the last node would know that it came from somewhere inside the network, know that it was going to a certain recipient, but not be able to correlate the sender and the receiver. I'll talk about that more a bit further. But during the 1980s, not much happened in the field of anonymity, with the exception of some work here in Germany, actually. But it was a little unfortunate that most of the papers were published in German, and we're still reinventing what Andreas Witzmann and his colleagues did. So if anyone actually has the time or inclination to help translate those old papers, it'll save us reinventing the wheel, because there's been much great work that gets published these days, and Andreas says, oh, I wrote that 10 years ago, see my thesis. That's kind of an aside here, but yes, help. But during the late 90s, with the associated crypto wars, PGP, cyberpunks, all of that, people revisited the issue of anonymity. And in 2000, there was a conference that started called PET, Privacy Enhancing Technologies Workshop. It's now turned into a symposium and is a lot more theoretical and focused on polished papers. In the beginning, it was more focused on practical uses and where we could go with these technologies, where we could go with mixed nets and so forth. And what I'm about to discuss here is a new class of primitives that I've been looking at using for anonymous communications that I'm hoping can be made as usable and ubiquitous as Tor has the potential to be. This isn't a philosophy talk, but there are reasons why people want anonymity. If there are some of those people here who say, screw anonymity, we'll cover this briefly. Generally, when people talk to each other, they don't presume there's going to be eavesdroppers. They like to be able to have communications that are between them and the person they're talking to. The internet has done a considerable amount to improve worldwide communication. We're all here together. Lots of you probably know each other from. How many of you here actually have met people that you've known online for the first time here? There are some hands, at least a dozen, more, yes. Right. How many people would not be here at CCC if it weren't for the internet, if it weren't for, So I don't need to tell you why the internet's good. I don't need to tell you why mass communication and global communication are good. It may be worth mentioning that the open kinds of communications we have are less likely to be as frank and open if what we're talking about is known to be watched and monitored by corporations and governments and pretty much anybody who can gain access to your network. If it's just that you don't want your sysadmin reading the letters that you're sending to your future wife, or if you're working inside of a corporation that's doing something evil, where evil is defined very subjectively, but they want to be able to actually report this without fear of losing their jobs or life or somewhere in between those. Just down to the simple exercise, the natural right of privacy. Anonymity plays a major role in that. If what you do and who you are is known, then you really don't have any privacy. I could talk for an entire hour on the philosophy issues here, but so could most of you, and I want to get to the tech. So let's take a walk through history. In the early 90s, the cyberpunks dug up the papers that Chom wrote, and Andreas and the other researchers, and decided to implement a rudimentary form of mixes. Now, as I gave you a brief overview in the few minutes earlier, a mix is a system of routers or nodes, I'll refer to them as mixes, where messages come in and are reordered with other messages. So you have a relatively steady flow of messages coming in, and the inputs and the outputs are not able to be correlated by somebody watching the mix as a black box. This is achieved through the use of public key crypto. You take your message and you encrypt it, possibly to your recipient, but you take the message that your recipient's going to receive, you encrypt it to the last node in the mix. Let's just take a 3-node chain here for an example. You encrypt it to node C. You encrypt that encrypted blob to node B. You encrypt that encrypted blob to node A. And then you send it to node A. Node A strips off the encryption and says, where does this go next? Looks at the routing information and sends it to node B. Node B strips off the encryption and says, where does this go next? Note that node B can only see that it came from node A, not that it came from you. And it sends it on to node C, who strips off the encryption there and says, oh, I have a message for the person you're sending it to, and that it came from node B. Now, what mixes you select are always random, and you're selecting a subset of all the mixes in the system. That's a problem in that there is the potential for you to select mixes that are all owned by the same entity, in which case you're screwed. Anonymity has screwed you. So the Cyberpunk mixes are critically broken. If you take the example I just gave and imagine that as physical envelopes, you can realize that that package gets bigger and bigger as you stuff it, and as it goes through, it shrinks. So that's information that can be used by an attacker. There are ways that we can handle that through the use of padding that is random and can't be distinguished between regular padded messages and fully encrypted messages. In 1995, Lance Cottrell, who went on to found Anonymizer.com, wrote Mixmaster, which corrected numerous of the flaws in the PGP-based cyberpunk remailers, the most prominent being the padding issue. All Mixmaster messages are of a standard fixed size. You have 10K of payload for your message and essentially 32K of padding and headers and extra encryption information so that all the messages that are actually going through the network are all that fixed 32K size. And somebody watching this system is not able to tell, just watching the traffic, which message, where in the process of being sent through these chains a message is. There's another problem in the Cyberpunk systems that Mixmaster solves by completely avoiding and removing the functionality. Which I'll get to in another slide, apparently. So yes, problems with Cyberpunk mixes. You have a general lack of threat model here. They implemented the basic premise of creating your nested messages, but they ignore a lot of the attacks that were hinted at in the original paper. It's an ACM paper, 1981, if you want to dig it up. Very short paper, but it manages to pack in a lot of the attacks that it took us the last 7 or so years to really understand. Replay attacks are a big issue here. If you are an attacker and you can grab one of these messages as it's passing through the network and send it through again, the servers that will process it will happily process it again as they originally did, and if you keep doing this, you'll be able to learn what that message actually means. If you catch me sending a message into the network and you grab my encrypted blob and you can watch various parts of the network and then insert my encrypted message again and again and again, eventually you realize that this gentleman here keeps getting all these identical messages, and wow, it must have been the one I was sending. Mixmaster solves that by keeping a running list of the hashes of messages that have gone through each mix and discarding ones that are replays or ones that are over a certain amount of time old. It's default 7 days, I believe. The Cyberpunk-based mixes implement a way to receive messages synonymously, and therefore cannot implement that sort of protection. Mixmaster, because it implements that sort of protection, does not allow for the NIM server-based receiving of messages. A brief digression here. The way that works essentially is you wrap your return address information in a nested payload so that an email comes into a NIM server, such as nim.alias.net, and on that NIM server for your account, johndoe@nim.alias.net, there is routing instructions encrypted to various nodes. So the message comes in, it's encrypted, it gets this routing information attached to the top of it, and then that's sent to the predetermined nodes or mixes that you've selected. And so Mixmaster, as I said here, it avoids the replay attacks, but you can't use it to receive messages. You can only send messages, so the usefulness of that is not as great. It does introduce a number of concepts that were missing from the original paper, as well as from the original Cyberpunk systems, such as cover traffic, detection of attacks, and so forth. Furthermore, it's a Unix tool. It's ncurses based. There's some Windows 95 email clients that support it, but that's about it. If there's any GUI developers here that have a passion for anonymity or after leaving my talk would like to work on GUI stuff, please talk to me. And of course, we're talking about mixes here that come in The Mixmaster system is a pool-based mix. Essentially, what you have is your message comes in, and it will sit in the pool for a minimum amount of time. And the pool will flush at various periodic intervals. And it will send a percentage of the pool at these various intervals. That percentage actually is not a fixed number, because there's attacks we've discovered, such as a flushing attack, where someone can flood a mix with all of their own messages so that they can sandbox the message they're looking for and just watch as the messages go through, see, oh, that's my message, that's my message, that's my message, that's a message I don't know, that must be the message I'm interested in, that's my message, that's my message, that's my message. And you end up with an anonymity set, it's a term of the field, of 1, yourself, because the attacker is controlling all the other messages. So the practical implication of this is that Mixmaster essentially has about a 30-minute latency. That doesn't really work for much more than email, Usenet, blog posts, things that don't have to be real time. You can't do web browsing over Mixmaster. However, the fundamental principles behind mixes led to and were extended and helped influence the development of onion routing and Tor and so forth. And that's really where I'm hoping the primitives that I'm going to talk about for the bulk of my talk will be taken. The current state of the art with low latency mixes, we have the original onion router system, which wasn't really deployed, ZKS Freedom, which was a commercial endeavor that did essentially what Tor does, but they tried to make money off of it, and that didn't really work when people started downloading lots of porn and they were paying bandwidth charges for each node. Tor and Yap. These are the two big players in the low latency field right now, and they're both broken. However, they're useful. You can actually use them to download web pages, to talk on IRC without waiting a half an hour for each packet to go through. The problem here is you apply information theory, you do some traffic analysis, and you lose. Tor has had probably 24 papers published in the last couple of years on various ways of breaking it. Yap, well, the designers of Yap conveniently backdoored it a while back, so confidence in that should be nil, because with Yap you have a fixed cascade of routes. A, B, and C are always the same order. They aren't up to the individual users, and they're all controlled by approved entities. I can't talk about all the attacks on Tor because that would take me about 6 hours, but if you go to this site here, you will see numerous papers on this. Yes, Yap has been renamed John Doe because apparently this was an offensive name to some people. You have problems with these things because you can't have operators that just come in and set up their system and start working. There needs to be a central service, either a manual approval process or an automated registry process. And yes, as I mentioned, central control leads to backdoors. Problems with backdoors. Well, if you have any single trusted component, and to quote Ross Anderson, a trusted component is something that can break your security. It's not to be confused with trustworthy. Then you put yourself at risk for both legal and hacking attacks. From a design and implementation standpoint, they're the same thing. Whether it's answering subpoenas or going to jail, or somebody breaking into your system and stealing your privileged data, it doesn't really matter. It's the same sort of thing. You can be a bad guy yourself running this system, or you can be a good guy who is coerced or secretly subverted. If there's any such attack like that, all of your users lose. Probably the first and most widely used anonymity system for email was anon.pennant.phi. It met its demise when the Church of Scientology managed to convince the Finnish government to get a number of the user accounts handed over to them because they were all stored in a mapping of anon123 at anon.pennant.phi, redirects to this real address. However, I've been told by a number of people that people in the underground hacking scene had that entire mapping for years before that. So we don't want to have trusted components. So we're working on improving Tor because people are using it. It's useful. It actually does provide utility for many threat models, just not strong adversaries. So any incremental improvements we can make to make that stronger, that's good. But we're also looking at developing systems that are based on fundamentally new primitives, different paradigms for achieving anonymity. And since it's a lot easier to design these systems when you don't have to worry about making it fast, we're focusing on the low latency email use case first. My hope, and the hope of the people that are working with me on this, is that once we solve this for the low latency email and so forth use case, we can then extend these primitives to become a high latency use case, extend these primitives to become a low latency use case that works for real-time transactions. As I mentioned before, reply blocks are fucked. You can check this out in a paper from 2005 published at WPES, called the Pinchon Gate. There is a section in there, 4.2, hear your laptops clacking. Essentially, with the reply block-based system that I mentioned before, where you have a NIM server that stores this encrypted, nested return address information, an adversary watching the traffic can correlate inputs coming into John Doe at nim.alias.net and outputs going to his personal account over time. And while one instance of a message going through is mixed well enough that the attacker can't know who it was, what we're working with here is the principle of the anonymity set. How many other users, how many other real individual people are actively receiving mail at the same time as you? Let's say there are 10,000 users of this system, but at any given time, 1,000 users are receiving mail. That means on the first round, your anonymity set is 1,000. On the next round, those 1,000 people may be a different set of 1,000 people. And as you can see, over time, you perform intersections, you rule out who was in this round that's not in this round, and you knock them off the list. And our calculations based on the level of spam in 2005 led us to believe that if you have a reply block account, it is guaranteed broken by an adversary who can watch the network within a month. I just recently read some data on the rate of increase of spam in the last year, so I suspect it would probably be a few days at this point. So the primitive that we're working with here, that we're trying to address these problems with, is called private information retrieval. It's a subset of oblivious transfer. It's been known since 1995. My co-authors and I actually reinvented it and then realized, wow, this field exists and there's been lots of progress in it. But all of the papers since 1995 up through the one we published on using this for email kind of hand-waved the use case. This is an interesting crypto primitive, information theory primitive, and it's probably important for something, maybe healthcare protection. I don't see how it can be used for healthcare databases, but we have a prototype of this as a basis for an email pseudonym server. So in our system, we're using Mixminion, which is the next generation of Mixmaster. It improves some of the flaws in Mixmaster. For transmission of emails, we're retaining the mix-based sending, because that's not completely broken. But we're replacing the message retrieval aspects. So we have our forward anonymity system, and users need to be able to get mail anonymously. Furthermore, it needs to be usable. It needs to interface with your email clients. You're not going to want to switch email clients every time you want to be anonymous. Our system uses the simple XOR scheme that Tor presented in 1995. It's a distributed trust system where you have multiple entities all running nodes. In this case, they're not mixes, they're databases. If all of these databases that you're querying collude, you're screwed. But if even one is not in collusion with the others, you're okay. And note, this doesn't mean that they all need to be good guys. It's all right for them all to be bad guys, just as long as they're not bad guys who get along with each other. I'd be perfectly happy to use a system that had the US TSA running one of the nodes and Al-Qaeda running the other one. I don't trust either of them, but they're not going to talk to each other. I trust that they're not going to collude. So, our threat model. Defining a threat model is important before you design a system, otherwise you don't know what you're protecting against. Our threat model is we have an active attacker. Somebody who can actually submit messages, perhaps delay messages, perform flooding attacks, and so forth. This is actually a stronger threat model than the passive attacker, where the attacker is just able to watch things on the network. We assume he can see the entire network. This is not such an absurd assumption when you look at the map of how the telecommunications systems work. Pretty much everything flows through Western Europe or the US. And you could have multiple governments, multiple ISPs, individuals working in any of these governments or ISPs doing the monitoring. So we assume, and of course, these routers could be owned by some unknown entity. It doesn't have to be the governments or the ISPs we're worried about. It's merely the bottlenecks where this information comes together. But we assume that the attacker can see everything on the network. And we assume that he can also operate some of the nodes. If we institute a process like YAP has, where node operators must be approved, then the whole system can be subverted. The principles behind Mixmaster, behind Tor, etc., are that anyone can set up a node, anyone can operate it. If you don't trust the system, run a node yourself, and now you trust that node. This, unfortunately, leads to the fact that the bad guys can run nodes too. So we have to design a system that takes that into account. So the architecture of the Pinchon Gate system is similar to the reply block-based NIM servers like nim.alias.net, where senders send mail to the NIM server, which encrypts them and sends it to what we call the collator here, which essentially creates a structured database in a 3-level hash tree and pushes it out, the entire database, to multiple distributors. These distributors contain the data in buckets. Buckets are simply blocks of data that are referred to. The recipient down here has a nice little invisible client that performs the private information retrieval operations that I'll describe in a minute to a subset of the distributors, and is safe as long as any one of these distributors is honest, or is not in collusion with the others, rather. And then, of course, we make use of mixed nets for forward communication, anonymous sending, as well as control messages. So, jump back there for 1 minute. Let's see that. Our NIM server contains some crypto foo here. We have a long-term public key for the authentication of control messages, and we have short-term shared secrets that allow for forward secrecy. This is in the slides on the site. You can check out our math, make sure it's right. But what we're doing here is creating one-time user IDs that are deterministic to the user, but don't allow an adversary to link the user's previous session with his session today or with his session later. The NIM server, pretty much throughout the entire system, we throw out any data that doesn't need to be retained. We've designed this so that the NIM server and the collator can be split off onto separate servers. They are separate software components. I'm a big fan of non-monolithic software, but they could live on the same machine, and they could actually be implemented as the same application if you wanted to. The collator creates this structured database which has, at the bottom of the tree, the leaf nodes are the message buckets that contain part of your message, all of your message plus some additional message, a single message by itself, the actual data you're interested in. The next level above that are indexes that point you at the bucket you're looking for, and then the meta index is what contains the list of indexes, and that is distributed as a hash from the collator so that you can be certain that for any bucket you're receiving from the distributors, you can verify this hash tree and make sure that you're actually receiving the real data. Because there's an attack here that, if you think about it for a few minutes, is obvious. If a distributor decides it wants to send slightly modified data to some subset of users so that it can distinguish between them, they'll end up losing. So we need to have a way for the client to be able to tell whether it's actually getting the true data from these distributors. Here's a nice little picture of it. What the PIR-based system does essentially is make the send everything everywhere approach feasible. If you had, let's take for example an anonymity system here where everybody in this room wants to communicate anonymously. We put up a bulletin board, and you guys have your own unique IDs that you can figure out, so you know who's sending, what's for you on this bulletin board. You have your pseudonyms. Everything gets up there. You take copies of that whole bulletin board, and you sift through it looking for your messages. This obviously doesn't scale. So we're trying to retain the security properties of that and make it practical. So in our system, we have each client, each user that's there, each user grabs a number of messages each day. If there's more messages waiting for him on the servers, it's delayed until the next day. What happens if there's too many to actually delay it? We have a system in there that's sort of like IMAP, where you can pick and choose to delete messages and clear out your queue. But if you get less messages than you're expecting, you just wind up with garbage, extra padding. And the point behind this is to protect against traffic analysis. You want to be receiving a fixed amount of data every day so that an observer watching the network does not even have to be an active attacker, just a passive one. If the volume of email you're receiving per day differs, he can correlate the amount of email coming into the name server with the amount of data you're retrieving. So that needs to be completely fixed. All of these distributors, in my diagram, the ones that the client are talking to, they all have the same copy of the same database that's updated daily, and they are all mutually untrusted. Our client is designed as a local shim. You point your email client at it over POP or IMAP and talk to it as though it's a mail delivery server. And in the background, it does its PIR requests to the database. So, what is this PIR protocol you keep talking about, Len? There's a number of different, more efficient PIR protocols we could have used, but we've picked this one because it's good enough for our use case, fast enough for email, and it's pretty trivial to analyze and see the security properties here. You pick L distributors out of the subset of distributors in the system, such that that L is large enough that you predict that there's no chance, or very little chance, that those distributors are all in collusion. So let's, for the simple case, say there's 5. You will create 4 completely random bit strings that are of the length of the number of buckets in the database. That's known. Let's say there's 1 million buckets. So you're creating 4 1 million bit long bit strings and a 5th bit string, such that when you XOR all 5 bit strings together, you end up with a 1 in the position of the bucket you want and zeros everywhere else. You submit those bit strings in randomized order. Obviously, you don't submit the special one last all the time, to the distributors. And they XOR, they'll get a bit string that has roughly half the bits in the one position. They will XOR all of those buckets together and return you the XORed blob. Each one of these databases will do this, and because of the magic of XOR, you take your 5 responses and XOR them all together, and bam, there's the bucket you want. Does everyone get that? See, this is your first bucket, or your first bit string. Yeah, some random numbers there that I randomly typed in. Your second one, your third one, and so on, with the last one being specially crafted such that it's the bucket in position 1, 2, 3, 4, position 5 that you're looking for, out of 1 million in our example. The nice thing about this here is that you've got some scaling options. If disk space is cheap, you can have a whole lot more buckets, because if you double the number of buckets, you have the number of bits in the bit stream. So you save on bandwidth. I threw this in here because one of my co-authors is a big fan of cat macros. Some additional concerns. All the users need to behave consistently. This is obvious. If you have one user who's just every 5 minutes hitting the check my messages button, he's going to stand out. You need to actually make sure that you're behaving identically to everybody else in the system, and that's a big problem with Tor. For example, no one using Tor behaves like anybody else using Tor. It's just not possible with that system right now. It's also a problem with Mixmaster to a slightly lesser extent, but still, it's there. So for our system, we are saying you can get new messages once a day. Yes, that's slow, but it allows us to spread out these requests over a random period within the 24 hours. All the users are making a single request each day for a identically sized bucket each day, and we're protecting the communication using TLS between the user and the distributors, so that you actually have to be running a distributor to learn any information here at all. And using the proxy-based approach, we're hiding all of this crypto stuff from the user. It's neat and fun to play with crypto, and most of you guys here could probably do it easily, but if we're worried about journalists in third world countries, human rights workers, your grandmother, you can't expect them to understand this. So we want a client they can install, and it will just work. I mentioned briefly earlier the IMAP style communication. Buckets include this summary message here that says what's in the queue, what's waiting if there was anything delayed, and there's mechanisms for them to say, I want that message next, or dump those 5 messages, they're obviously spam, etc. But there's some problems. Our first paper had a big problem here. It was secure, but trivially breakable in the denial of service area, because if one of these distributors decided it wanted to screw the pooch, it could just return garbage data all the time. And since you're getting garbage data, essentially, until you perform the XOR and get the bucket you're looking for, you can't tell which is which. So we detect that when it happens by following the hash tree, going, whoop, this doesn't match, and the user doesn't get his mail. But how do we know which distributor that was? So there have been some other approaches. Babel Install came up with a system. Goldberg improved upon it performance-wise that uses polynomial interpolation to get you a system that allows for a certain number of distributors to be corrupt and try to deny service, and you can still recover your data, but that actually weakens the security because now you don't need L-1 to be bad, you need just that K subset of L. Our solution sits at the higher level. We introduce a piece called the validator, which is currently a separate component, but we're working on integrating this into each distributor. And we do this at the cost of double the network communications because we use a cut and choose protocol. Instead of sending one set of bit strings, we send 2. There's the alpha set, which is what we actually care about, and the eta set, which is a challenge. And a distributor wanting to screw things up can either just send back garbage for both requests, and then he gets detected. He can send back garbage for only one of the requests, and in that case, he either succeeds or fails, but he's going to get caught eventually, rather quickly, actually. If there's enough users to be using this system to actually make it secure, in that there's people you could hide amongst in your anonymity set, then it's going to be reported that this distributor has a problem. I have 15 left, or I'm, OK. So we randomize the alpha and eta, of course, so that he can't tell which one he should be tampering with. And this really is a problem that isn't so much implemented for the purpose of protecting against malicious people. It's more our own debugging. And what if somebody's running a system that has endiness problems, or there's network communication errors on that server, or the incompetence aspect of this is greater than the malice aspect. But if there's a problem, we can then send the entire data set up to the verifier, and he will tell us which one was wrong. One at a time, we send those bit strings. We get the responses back, and they should match identically what we got back from the other distributors. So we're obviously caching this information when we send it to the distributors. For the one that's a mismatch, well, that's the distributor that was bad. If there is no mismatch, they were doing the 50-50 thing and they guessed right. Let's catch them next time. So yes, you can worry about framing people, but yeah, the validator can frame people, but since we're randomizing the bit strings we're sending to the validator, it's really hard to frame a given distributor consistently. Currently, the validator is being run by the same entity as the collator, so it really serves no purpose for the validator to try to perform denial of service attacks, because the collator could simply do that by turning itself off. We don't trust the collator and NIM server components for our security, but we do presume that they're not going to deny service to us. If the NIM server and the collator don't work, then the system doesn't work. Yeah, I covered that already. So, where would I want to go from here? Well, about 10 years ago, we had Mixmaster. We had gotten some of the big problems of mixes solved. We'd figured out how to use this in a fairly secure fashion for sending mail. And that evolved, not directly, but inspired the circuit-based anonymity systems that you see in Tor. We'd like to have, the first step, a forward message transmission protocol based on PIR. Currently working on that. Eliminate the mix aspect of it altogether and send messages using PIR. And then from there, let's extend that to low latency solutions. Let's get rid of this whole nested encryption mix crap that can be broken using traffic analysis techniques from the 1940s and come up with an information theoretically secure, low latency solution that can be used for web browsing. Some of my colleagues at Kazakh at Leuven are working on using PIR in the high latency cases for non-email based use cases. So hopefully we will be understanding PIR better in the coming years and able to work on making it faster and more broadly usable. The client proxy actually is a really tricky component because it has to be really invisible. It has to be something that the user can simply install and forget about, and doesn't need much maintenance, because privacy is not something people want. They don't want to install a privacy program to use it. They have this general notion of wanting privacy, but we all know that people don't want to work for it. So let's make it so they don't have to work for it. Let's build these really easy to use invisible proxy shims and come up with good GUI HCI components that let them forget about it. Help, GUI developers, talk to me, please. I'm going to jump right to questions since I have 8 minutes left. Are there any? I breezed over a lot of that stuff there, so if there's anything you'd like me to talk about in more depth. No questions at all. Ah, there's one.
You mentioned to pad the traffic on the servers. Wouldn't that be detectable in the same way as the clock skew of Tor servers is detectable?
Is Stephen Murdoch here? I know he's here. So which aspect of the padding are you talking about?
You want to pad the traffic amount to a fixed size. So you have to generate a padding on the server to get the same amount. And that is workload on the server.
Yes. However, this is not a... So the question is, can you use side channel attacks? Can you predict something about the padding on the servers to learn information about what's being sent? The gentleman who brought this up referenced the paper called Hot or Not by Stephen Murdoch, which performed an attack on Tor by looking at the clock skews of messages going through with hidden services. It doesn't apply in this case because we're not... First of all, that was an active attack. That was, it implied that you could actually watch the traffic going through the Tor nodes and determine things about the various, the clock skew. Here we have a situation where you have these buckets coming in, and you have data being put into the buckets, and it's split. The padding actually in our initial test case is real mail. It's other people's data, and it's all done on the collator's side, not on the individual distributors. So there is no obvious correlation between that attack you mentioned and what you're referencing. How you do your padding is a very strong concern. If your padding is distinguishable from real data, you're screwed. But there are safe ways of doing padding. Most crypto primitives, such as RSA, rely on strong padding. So we're using some of the PKCS padding systems, and if they're broken, there's a whole lot more in the world of crypto that's broken. If you can figure out a way to attack my system here based on that, please tell me. But it's a different animal because of the fact that it's padding that's done at the leisure of the collator sometime during this 24-hour period. It's constructed in a cryptographically random way, and furthermore, the data is all transferred, encrypted over TLS. So there's not much potential for attack there.
You talked about Tor a whole lot. Are you familiar with, and could you compare your system to I2P or OTR?
I'm sorry, I2P and what?
OTR, off the record?
I helped with the design of OTR. That's an entirely different use case.
Okay.
I don't mean that I helped design it. I proofed the initial paper before it was submitted. But that's comparable to PGP as far as what it tries to do. It's a communication protocol not for protecting traffic analysis, not for keeping people anonymous, but for encrypting communications in a way that's authenticatable between the parties, but reputable, so that Alice and Bob know that either Alice or Bob sent it, but can't prove to Mr. Judge that any given one of them did. That's a different, apples and oranges there. I2P is broken. It's just a mess. That's an entirely different talk by itself. But yeah, Tor is less broken than I2P. There is a last question over there. Yeah? Talking more about the padding briefly while our microphone makes its way over to the back. You're too far. Right here. Right below my dot. Padding is a very tricky area. You don't want the ability for an attacker to flip a bit in an unnecessary area, in the padding perhaps, that can propagate through the system and then be detected in the clear text. That's why we're so concerned about making sure these hashes match up and rejecting anything that doesn't, because there's this class of attacks called tagging attacks that you can look up on freehaven.net/nonbib, and that'll go into that deeper. Question.
The question I had is, it was to ask me, how do the
Speak into the microphone louder, please.
How do the clients communicate with the first server? So for me, it seems like there was one central server which splits it up to the small ones.
These distributors all have the same size database as the collator.
So, but where do you go into the network? So, is it one main server for all the other distributors?
Yes, there is a single collator or a load-balanced set of collators that handles your email addresses. Since this is based on email, there has to be a place that email goes, and that's one service. Currently, you sign up through it using Mixminion or Mixmaster to send your anonymous messages to create your account on the NIM server, and then later you start querying the databases with your.
So then you always use the same NIM server for your messages?
Yes, but you never talk to the NIM server to get your data. You talk to the distributors. You only talk to the NIM server to set up your account and to make changes to your account. For more of the gritty details on this, I refer you guys to the paper that is up on freehaven.net/nonbib from 2005. It's by me, Len Sassaman, Bram Cohen, and Nick Matheson, called the Pinchon Gate. Any last questions? No? Okay, thank you very much.